going to talk about how much force is on that single tendon, that half-centimeter diameter tendon, in order for Arnold Schwarzenegger to do the strict bicep curl. But we're actually going to talk about the world record holders, because he's not actually the record holder. So to understand this problem, we're going to have to come back to equilibrium. And this is kind of the physicist's weightlifting regime. Okay? Back to equations. So for an extended object to be in equilibrium, we already know this one. The net force has to be 0. That implies that the acceleration has to be 0. So like the translational acceleration has to be 0. And now we're going to add to this the real full equilibrium, or total equilibrium. The net torque on that object also has to be 0. So we're going to define something called total equilibrium of a mechanical system as one in which the net torque and the net force are all equal to 0. Okay? Now, when we said this before, when we had equilibrium, when we were just talking about forces, we said that there's also dynamic equilibrium. I could have a constant velocity. That's still going to be the case here. I can have an object that has a constant velocity and still be in equilibrium as long as the acceleration is 0. So the strict statement of total equilibrium is that the total force and the total torque has to be 0. Okay? So let's think of an example where this isn't quite right. And here's one. If you think about a box with 2 equal forces acting on it, this is a problem that we've dealt with quite a lot. If you summed up the forces on this box, you would immediately say that that box is in equilibrium, because the sum of forces goes to 0, right? The length of the vector to the right is exactly equal and opposite the length of the vector to the left. So if I had 2 pieces of rope and I was pulling on this block with equal force, it would not accelerate, and we define that as equilibrium. Okay? But you could apply those 2 forces somewhat differently, like this. What would you get? If I took a rope and I tied it kind of towards the top corner of this one, but the bottom corner of this one, and I applied those forces, you would rotate. In which direction would this thing rotate if I did it just as in the diagram? You kind of see those arrows, right? It's going to go clockwise. So this object has a net torque on it. So we would say that in this picture, when I apply the forces like this, it's not in total equilibrium. Right? I can apply these forces and they would build a torque. It's not equal to 0. So the question is, when we think about complex objects, we have to say that the only way that that object will stay in place and not rotate is when the sum of forces and the sum of torques are all equal to 0. Okay? And we'll talk about all the special cases, which is just like what we saw before. So a special case is what we'll call static equilibrium, where the velocity of the object and the angular velocity are equal to 0. If I have a wheel like this one, if I have a wheel that is moving at a constant velocity, let's say I had a frictionless wheel out in space, and it's at a constant velocity this thing is rotating, the sum of torques is still 0, and it's actually in dynamic rotational equilibrium, right? If I have an acceleration that changes its angular velocity, then I have an acceleration. So there's this analog, just like in this, Newton's law in linear coordinates, it's the same thing here. So the object is at rest and is not rotating, which is called static, but equilibrium simply means constant motion and rotation. So there are special cases where we'll say everything is completely static. That's a special case with a more general case, that the acceleration is equal to 0 and the angular acceleration is equal to 0. So think of a really simple example. Let's just take a hammer, and I'm going to say, you'll see these symbols a lot as we talk about some of these examples. You'll see this little symbol here, that means kind of the center of mass. And we're going to talk about that at the end of today and next time, how you find that. But imagine I have a hammer, and it's basically being held in space by some normal forces. I have the weight acting on the center of mass of the hammer. But then I have these 2 forces that I've labeled, N sub A and N sub B, that are holding it in place. What can we say about the sum of forces if we know this hammer is standing still? What would you say? You would say that the sum of this force and this force has to be equal and opposite the weight. Right? The sum of forces has to be 0. If suddenly this weight force was bigger than it is in this drawing, this hammer would fall. Okay? There would be an acceleration. So this is a picture of this hammer in equilibrium. And we can now ask, let's think about all these different ways that this hammer could rotate. It could rotate about any point, really. And equilibrium tells us that the sum of the torques has to be 0 in order for this hammer to stay still. Now, there's a weird thing, and this comes into problem solving. We'll see it in an example today. No matter which point I choose as my pivot point, right? So you could imagine this hammer pivoting around A, so it would rotate in a clockwise fashion. You can imagine it rotating around B, either clockwise or counterclockwise. But when I do the mathematics and I apply Newton's second law to sum up all the torques, it doesn't matter which point I choose. Okay? I can choose even this weird point out here. I know that the only way this hammer stays still is if all the sum of all forces is equal to 0 and the sum of all torques is equal to 0. Okay? So that's going to be our definition. And we're going to handle some problems today. And just like we always do, you have to start with thinking about the motion. So I'm going to give you a really quite complicated one just as a workout to warm up. And then we'll start talking about C.T. Fletcher and Arnold Schwarzenegger's bicep again. So here's the first thing we do. Say you're given a complicated question or a complicated situation. This is the same as applying Newton's second law and third law. You first think about how this object would move. So you imagine what would happen. And then you model the object as a very simple shape. So you don't use all the complicated stuff, you simplify it. And you'll see this in a few examples today. You draw a visual overview that shows all the forces. And for torque, we need to know the distances from the pivot point. You remember that torque is the radius from the pivot point, so the distance from the pivot point times the perpendicular force at that point. So we need to know in these pictures now what these distances are. And so then you write down, just like you would in any problem solving, all the things that you know, right? What's given in the problem. Now this is, just like in the forces, this is the key part. You pick an axis, so you define where my x-axis is and my y-axis is, or a pivot about which the torques are calculated. So you get to pick one point in the problem that you think this thing would rotate around. And it can be anywhere. It's just that sometimes it's more convenient to choose certain points, and we'll talk about this. Then you determine the torque about that pivot point with each force. So this is a calculation of R, F perpendiculars. Find all those terms, whether they're positive or negative. And the torques due to any forces acting at the pivot are always 0. So this again sounds things that we've been practicing. And then you determine the sign of each torque. This we really now are experts. If this thing, I have a pivot point and I imagine it to rotate in the, for you guys, counterclockwise direction, we know that that's, okay, this is that's clockwise. If it rotates in the clockwise direction to you, you would typically call that a negative torque. If it rotates counterclockwise, that's what you would call a positive torque. And that's our convention. So the math steps are based on the fact that an object in static equilibrium has no net force and no net torque. So you write these equations down, you solve for the total torque and the total force, and you have a set of equations from which to solve the problem. You write those equations down, and you have to remember one really important thing, is that the forces are vector components, so you have the sum of forces in the x and the sum of forces in the y. You can test it on this. This is kind of old hat, but we'll add to this the sum of all torque. And then you go through and you solve the equations. Okay? So this is our basic recipe. You start with some complicated situation and you simplify it to a cartoon. You then apply Newton's second law. So this should be somewhat familiar. The only challenge is these problems can be really complicated. So this is our first example. So imagine, this is a really common example. I could do it with this ruler. If I lean a ladder or this ruler against the wall, you can ask me a really simple question, which is, at the angle that I hold it, when I let this go, maybe I'll move out here so you can see a little bit. When I let this go, will it slide or not? Right now, there's not much of a coefficient of friction, of static friction between the ruler. So when I let it go, it seems a bit. Let's see. Okay. At a certain angle, it will fall. I can actually play a game with that angle, right? If it's really steep, if it's right up against the wall, it probably won't fall. If it's out here, it's probably more likely to fall. Okay? So this is a really complicated problem because it's not obvious how we can think about rotation, right? The ruler's rotating in its own reference frame, but in fact, when you think about what actually happens, it's sliding. Okay? So the center of mass is moving. There's some rotation in the problem, but we have to simplify it to ask this question. What is the minimum value of this coefficient of static friction to make this thing not slide? Okay? It turns out that when we solve this carefully, the number of steps is actually quite few. Okay, so let's try it. Much fewer than the one we did last time. So let me just start this. I'll put it out here. I'll leave the question in the middle. So I'm just going to go through this like this was a problem in your exam or on the textbook, whatever. The first thing I would do is I would say, okay, well, let me draw. So they've given this kind of complicated picture with too much information. So I want to digest it myself to really understand what's going on. So the first thing I do is I just redrew it. Really simply, I have a ladder of length L at some angle theta, and there's a distance d1, which is the distance labeled in the picture they gave us, which is basically the distance from the pivot to where that point is of the center of mass. You see that it's the center of mass, the weight is pointed down, and there's this distance. So I've simplified it just to look at one thing, which is the geometry. And I've defined my axes as positive x, positive y, kind of the standard way. And then I said, okay, I want to just, for later, it turns out we'll need this, but I just want to look at this. You often see these triangles, right? If I look at this triangle, I have a triangle made from L, the line opposite the angle, and then D1. So I can just write down this relationship. The length D1 is actually equal to L over 2 cosine theta. That just comes from trigonometry of this little triangle that I made. L over 2 is that side of the triangle. D1 is that side. The cosine gives me cut, adjacent over hypotenuse, and so I rewrite this geometry. Okay? So there's a relationship between D1 and F that will come back. Any questions with that? This stuff you're getting better and better at, and I think you're probably quite confident that you can do it. But then I have to ask, how does this thing stick? If the question says, what is the minimum value in order for the ladder to stay fixed? The statement that it stays fixed is exactly this, that the sum of all forces is equal to 0 and the sum of all torque in the problem is equal to 0. So this is our statement of equilibrium, and now we have to just carefully understand how to write these things. So I'm going to redraw it really quickly. Again, it's the same picture that you see above. I've just kind of taken a few pieces out of it to make it a little bit easier. This is my diagram that shows all the forces acting on the object. Okay? So the first one, and you'll see all of these forces in arrows on the original diagram, but I just drew it to simplify it because there's a lot of information. So the first one is that there's a weight, right, at the center of mass. This ruler or a ladder has some mass, so it has the force of gravity acting down. There's a normal force of the wall pointed on the ruler, so it's pushing out. The ruler is equally and oppositely pushing into the wall. And I'll call that this normal 2, just like they did in the diagram. There's a normal force of the floor on the ruler called N1. Now, going back to this ruler that I was holding, if I had this ruler and I wanted it to lay against the wall, which way was it sliding? To you guys, it's sliding positive or negative x? Positive x, right? So which way would the friction force have to act to stop? Negative, okay? And that's just what you see right there. That the force is pointed to the left, and I've kind of drawn it on there. It's overlapped with the axis, but that's the force of static friction. Are there any other forces that you can think of in the problem? Maybe, but none that are important, right? You could probably cook up something, but it's not actually relevant to solving this problem, okay? So, now I have a diagram and geometry, so I have triangles and angles and all of those things, and I just have to execute. I have to start writing down these equations. Now the first 2 equations, I think you're going to have no trouble believing. So the first equation is I'm going to take the sum of forces in the x direction. I'm having trouble. Okay, so the sum of forces in the x direction. Why is it so blurry? Hold on. It's like I took off my glasses, but I have them on. Okay, Okay. So the sum of forces in the x direction, if I look at this picture, which forces on this act in the x direction at all? There's only two of them. The forces in these are actually pretty easy. They're all either x or y. So I have the force of static friction, and I have N2. And so the sum of forces in the x direction is N2, which I call positive, minus the force of static friction, and I know that that has to be 0. Okay? That's just equilibrium. I do the same thing in the y direction. And again, really straightforward. You've done this before. I have N1 pointed up in the positive direction, I have weight pointed down, and this tells me it has to be 0, and I get a relationship that N1 is equal to m times g, the mass of the lap. Okay? And then there's a third one, and this is where it might be a little trickier for you. I want to add up the torque, or torques, in the problems. Okay? And if you remember, there's several different ways to do this. One of them is if I have a ruler, let's assume that my pivot, so this ruler, I'm going to hold it just like in the diagram, it's at some angle. I'm going to assume that it's going to pivot around this point at the bottom. So as it slides out, in its own reference frame, do you see that it's rotated, right? So as it slides out, the action actually looks like this. But if I had a camera that lived right along that point, I would just see it rotating this way. Okay? So I'm going to assume that that's the pivot point, and that this thing rotates around that point, right? And then I'm going to write down the torque. So there's a few forces. So for instance, these two forces, Fs and N1, do they apply a torque if they're applied at the pivot point? No. Okay? So here's the first trick. When I'm thinking about a pivot point to choose, I'm going to choose the one that cancels out the most forces from the calculation. If I know that those forces are applied at that point, I don't have to put them into the equation. So the only two forces applying a torque are the force of gravity and N2. You see which direction around this pivot point, the weight or force of gravity, which way would it rotate the object? Clockwise or counterclockwise? If it's pivoting about this point, if I let this thing go with just the weight of the ruler, which way is it going to rotate? Counterclockwise. What do we call that? A positive torque or a negative torque? Positive. Okay? So the first term is basically d1 times the perpendicular distance to that. If you remember, you would have force times radius perpendicular or radius times force perpendicular. I'm going to show you both ways. The first way I would write this down is say that it's d1, this is the line of action, and perpendicular to that is the weight going down, okay, mg. The minus torque, N2, is going to be d2, which is the length called the line of action. d2 is the length parallel to the direction of that force, times N2. That one is rotating in every direction. This is maybe not the way you would solve it. I'll show you in the next step the more typical way that we think about it. And basically it looks like this. So I can actually rearrange number 3, so equation 3, in terms of L. And this should be exactly what you would get if you applied your normal definition of torque. Okay? There's the torque due to the mass, it's the weight equals mg, and then you have L cosine theta over 2. This is just finding the perpendicular force component to cause that rotation. And then you have the negative torque, which is just the contribution from N2, which is trying to rotate it in the clockwise direction. And I set it equal to 0. Okay? So that's all I've done. I've executed. Force in the x, forces in the y, forces or torques all equal to 0. And now I just have to do a little bit of algebra. So I simplify this equation, and I can solve for N2. So taking this term, take mg L cosine theta over 2L sine theta. This is just algebra. And I get this simple expression that the normal force, number 2, is just weight over 2 tangent of theta. And then I can go back to equation 1, which tells me that the static friction force, right here, equation 1, is equal to N2, which is what I just solved for. So the static friction force is mg over 2 tangent theta. And I need to find the static coefficient of friction. How do we write down the static friction force? What is it equal to? It has the normal force times this coefficient of friction, u sub s. So that's the last piece to the problem. if I draw this static friction force, if I write down the equation for it, it's always less than or equal to mu sub s times n1, which is the normal force, and that's equal to mu sub s times the weight, mg. Right? The normal force is just basically the weight of the object. And then I can write down, just by rearranging, that the static coefficient of friction is always greater than or equal to that frictional force over n1, or 1 over 2 tan. So when we have these coefficients, remember they're just numbers, and that works out. This is just a number. It just tells us that static coefficient has to be basically bigger than some number proportional to that angle. And I don't know what the angle is or the number, but you can actually solve it. In this problem, they give you 60 degrees, and so you get some real number. Okay. So all we've done here is basically apply 3 rules, and they were done right at the top. We take the sum of forces in the x direction, set them equal to 0, sum of forces in the y direction equal to 0, and sum of torque equal to 0. Do you think you could do this in a simpler situation? You'll have this homework problem or something very much like it, but can you do that basic calculation for something really simple? Let's give it a shot. Work with the people beside you. Here's a much simpler version. All you have to do in this problem is carefully apply those same rules. The sum of forces and the sum of torque equals 0. Okay? So draw this picture in front of you. Draw the forces. Remember all of Newton's laws. And see if you can draw this. Solve this problem. I'm going to deliver it, but I'll give you plenty of time. Take about 2 minutes. Draw free body diagrams. Imagine how this object would rotate. Choose which pivot point you want to calculate around. Calculate the sum of forces in the x direction. In this case, there are none. The sum of forces in the y direction, and the sum of all torque. See if you can actually calculate what does the scale read if I build this little object. This is much simpler than the previous one, but it requires the same pieces of information.
Okay, so that's the pivot. Yeah, so it's going to be. So yeah.
Let me stop you for a second just to do a quick thought experiment. Let's say that I basically have something really similar to this. This ruler is at a pivot point right at its center. Do you see that that's a very similar problem to what you have here? You could call this scale the pivot point. Okay? Let's say I called that scale the pivot point. And I had on the right side of this ruler, I had 1,000 Newton mass holding it down. Which direction would it rotate about that point if I had 1,000 Newton mass there? This way, right? That's basically clockwise, a negative torque. What would I have to do? How much force would I have to apply at this little bolt in order for the torque to be 0? Right? This is kind of easy because you know something about it. If I put 1,000 newtons on this side, how much would I have to put on the other side? 1,000. It would have to balance. So the sum of torque has to be 0 or balanced. It requires that there's a force here pointed down at 1,000 newtons. Okay? So now draw that force on your diagram. Have your free body diagram. You know that there's 1,000 Newton force right here pointing down. There's 1,000 Newton force pointing down here. How does this object stay in equilibrium? Doesn't fall. It stays fixed. Take another half a minute, see if you can draw that diagram. You should be able to submit answers too, so write your answer if you got one. Okay, 2 or 3 more seconds. The majority of you have it, but slight majority. Okay, take a couple more seconds. I see about 130. Okay, I'm going to stop. Okay, so right at the last minute, actually, a lot of you got the right answer. So 58% of you said C, that it's 2,000 newtons. Okay, why is that true? Let's make sure we understand it. Let's actually do it with this ruler. Let's say that I put these masses. I'm not going to use 1,000 newtons. I'll use a smaller number. But I'm going to build this same exact system. So here I have the same force acting on each side. This one is taking the place of that fastener that's holding the thing in place. If I have two forces down, each of 1,000 newtons, what does the force up have to be on any object? Let's say I had a box in free space, and there was 2,000 newtons of force pointed down. What would the force up have to be to keep it from accelerating? 2,000 in the opposite direction. The sum of all force has to equal, basically the forces down has to equal the forces up. So the force of this scale on the rod would be 2,000 newtons. And then Newton's third law tells us what? What's the force of the rod on the scale? 2,000 newtons. These are equal and opposite. So we basically now have applied Newton's second law for rotation, and Newton's third law to get the reading on the scale. Again, same set of executions. Sum of forces, sum of torques equals 0, and you get the answer, in this case, C. Okay? So about almost 60% of you actually got that. There's still a large chunk who said 1,000. That's the most common wrong answer typically in this problem. We're going to come back to this one next time, and I want to make sure by then you understand it. Okay? I think you will. This is how this class goes. All right, let's talk about C.T. Fletcher. Anybody know C.T. Fletcher? Come on, you got to know. Okay. I can't show a video of C.T. Fletcher in this course. He's highly inappropriate, but you should go look at videos of C.T. Fletcher. He swears more than anybody I've ever heard in my whole life. He screams at his own muscles and tells them to grow. He's an awesome guy. But he, again, in 2015, he was the world record holder for something called the strict bicep curl. Okay? He has since been beaten. I'm not going to show a picture of this new guy, Dennis. There's a Russian named Dennis. He's also a world championship arm wrestler. He just beat him late in 2015. He beat C.T. Fletcher. C.T. had to get a heart transplant the next year, so he didn't compete. He's basically recovering from a heart transplant. He plans to actually recompete in a year or two from now. He's actually aiming to beat this guy Dennis for the strict bicep curl. Okay? So here's the question we can ask. In 2015, he set the record for strict bicep curl, which I'll define in a second, by lifting 102 kilograms. Does anybody know what that is in pounds? It's more than 200 pounds. It's something like 215 pounds, right? Who in here weighs more than, well, you're probably not going to admit it, 215 pounds, okay? I don't even weigh that much. He could basically curl me, and that would just be his kind of warm-up weight, okay? So he could pick me up with his two hands and just curl me, and it would be no problem for him, okay? That's insane, right? That is completely nuts. And there's a whole bunch of people competing for this ability, okay? So one question you can ask is how much tension is on that little tendon? This tendon is half a centimeter in diameter. Make that with your hand, half a centimeter. It's thinner than your pencil. And he's able to use that tendon and the muscle connected to it to create a tension that connects his bicep muscle to the bone to lift more than 200 pounds. Okay? So before we solve this, let me answer the second question, and this was something that comes up all the time, is how in the world do his skeletal bones stay together when he's putting this incredible tension on that bicep? So how much force is exerted by the elbow? If you ever look at the human body and how it's designed, it's actually very confusing the way we're defined. If I wanted to be really good at lifting heavy weights, where would I apply the tension force on this lever? I should have a tendon that attaches at the wrist. If my job was to lift heavy weights, the closer to the wrist I go, the easier it would be to pull. So if you're a power lifter, you often hear that shorter people have an advantage. I don't think it's really true, but people claim that because you're shorter, you have a smaller moment arm, and so you can lift larger weights given the length of your arms. So we're going to see why that is true in this problem with CT flexion. Okay? Let me draw the bicep. Let's do some heavy lifting, like the physicist version of heavy lifting. I'm going to keep him up here. You should really watch videos. He's amazing. Okay, let me draw for you really quickly what the bicep, how the bones and muscles look in everybody's bicep, or most of us. I'll try to do this somewhat accurately, but probably not great. That's your shoulder. This bone is kind of a funny one. Okay, so those are the bones of your arm. That's basically me in this position. Okay, shoulder down to elbow, forearm has 2 bones in it. Okay? I'm not going to draw the wrist, I'm not going to draw the hand because they're complicated, but I'm going to draw what the bicep muscle looks like. Okay? The bicep is called bicep because it connects in 2 places at the top. It's basically 2 terminations at the top. One is actually slightly under the armpit, connected to the rib cage. The other one's right underneath the deltoid, or the front of the shoulder. Okay? At the bottom, there's primarily this major tendon that holds it to the bone. So if you look at this bicep muscle, this is the muscle itself. And what it does is it uses the elbow as a pivot to lift my forearm. Okay? So here's my pivot point, P, my elbow, and it lifts that forearm muscle, or the forearm bone and muscle attachment. Now there's a distance between some of these things. The arm itself is about 35 centimeters. That's like from the elbow to the wrist. And then there's this distance between the pivot point and the point of connection of the bicep that is about 4 centimeters or so. And again, can you imagine the action of this arm? So the tension is applied to the bicep. I apply tension. It pulls up like a little puppeteer onto my forearm. Okay? Now, you can watch videos about this guy, this Russian dude, Dennis, or CT, talking about strict bicep curl. Nobody does it anymore. Does it? Anybody know the strict bicep curl? I didn't remember doing this. Okay. Here's the strict bicep curl, and I challenge all of you to try it. The strict bicep curl, everybody knows what a bicep curl is, right? This is pretty easy to know. Okay? The strict bicep curl requires 3 things to be in contact with the wall. Your butt, your shoulder blades, and the back of your head. These have to stay in contact with the wall. Why would that be harder? You ever watch these big tough guys in the gym? Yeah, you did it. These guys in the gym, they do this thing, right? That's cheat, right? That's a cheat. What the strict bicep takes away, the strict bicep curl takes away, is the ability to use momentum to lift those weights. So when you see them do it, they lift to here, their elbows stay right in at their rib cage. Only when they get to this position that we've drawn are they allowed to lift the elbows to bring the dumbbell up to their shoulder. Okay? The strict bicep curl is the right way to curl, in my opinion. It dominates all of your effort in the bicep. The bicep is basically the only thing working. Everything else is only stabilized. Okay? And you're not able to cheat. So like I said, the next time you go downstairs at the SRC and you see kind of the pit, and these guys are like, tell them just to stand against the wall and see if they can do it. And they won't be able to. Typically when you're doing the strict bicep curl, you're only able to do about half of what you're able to do with this kind of typical core elevated bicep curl. So these guys can do something like 400-pound curls if they wanted to thrust their hips and do a curl. Okay? It's nuts. It's completely nuts. Let me show you how nuts it is. Okay? So our question was, what is the tension in this tendon? And what is the force exerted by the elbow? So we can actually solve this. I'm going to draw something slightly different, which is the physicist's version of the bicep. And it looks like this. Okay? There's a physicist anatomy lesson. Okay? I have two rulers, right? Here's my pivot point. Here's my forearm. Here's my upper arm. Here's the force of tension that the bicep is applying to that forearm. Okay? And I have these distances. I said what they were. This is the distance to the tendon. This is the distance to the barbell at the end of the forearm. Okay? So this is the physicist version of the same problem, drawn really simply to try to solve it. Okay? Now, let me actually write this out for you. So we have that picture in mind. Keep it up there. And I'm going to just do the same thing we've been doing. Let's apply sum of forces is equal to 0 and sum of torque is equal to 0. So all we have to do here is take the sum of forces and the sum of all torque equal to 0. Right? So this is the same type of problem. We have some forces, we have some pivot points, and we're just asking about how they are drawn for equilibrium. So the sum of forces in the y direction are equal to the force of tension on the tendon minus the force of the elbow minus the force of the barbell. That equals 0. Does everybody see that? So I basically, in order for this thing to be in equilibrium, I have to have the tension pulling up, I have the barbell pushing down, but I have to have my elbow, my upper arm has to be pushing down, or else my arm would rotate. Okay? And we'll see that in the second half. I have to have the force of the elbow on the forearm to fix my arm in place for this problem. Now the sum of forces in the x direction, what is the sum of forces in the x direction? There are none. This one's easy, so there's 0. Okay? But now I can do the sum of the torque. So the torque is actually pretty easy in this problem. I have a force of tension. If my pivot point is the elbow, at which direction would the force of tension in the bicep rotate my forearm? You can see it. Which way is my bicep going to hold my forearm? It's in the positive direction. So I have a positive torque due to that one, and I have a negative torque due to the barbell. And I know these distances, right? So I have the force of the tension times this little d sub t minus the force of the barbell and d sub b. And that has to equal 0. Again, total torque has to equal 0. Now I can solve for this. I'm going to ask how much tension is in CT's elbow. This is the crazy part. So the force of tension, just from this equation, is equal to the force of the barbell times the distance over the distance to your tendon. And I'm just going to plug in some numbers. Okay? I'll let you do this, but it's actually pretty simple. M times G, we know the mass from the question. It says it's about 100 kilograms. We know G, it's 9.8 meters per second. And we know these distances, right? This is dB, and this is dt. These are just numbers. dt was 4 centimeters. dB was 35 centimeters, as we drew before. What I get from this is about